Good evening, everybody. My name is Dr. Gudimetla, and I am making a short presentation as part of the requirement for the selection of a senior lecturer position at CTU. So this following presentation deals with the presentation of a simple concept to my first year engineering students. The concept of discussion, or the topic of discussion, is to try and convey to students how we find out the stresses in a simple prismatic bar. Hi everybody, thank you for being here. The purpose of this discussion is to try and shed more light on the tensile testing experiment that you have conducted previously in the lab. So what we are going to do here is to try and create an extension of the simple and normal tensile stress that you have calculated by virtue of that experiment. So I would like to draw your attention to the prismatic bar that you see, where the blue anode axial load is acting on it. So what you have seen in the lab is when you take a cross section that is perpendicular to the face of the prism or the prismatic bar, you are able to quantify that as the normal reaction that the material is exerting to that load P. Can we quantify that by simply saying that it is the value of the load divided by the resisting cross section? So this is a very straightforward example of the direct normal stress. However, there can occur instances, particularly in the case of your beams, where forces need not act perpendicular to the face of a given beam, and thereby there can be a reaction which has to be equal and opposite to the direction of application of that force. So to try and analyze these kind of cases, say if we take any type of arbitrary plane as shown, okay, so this is obviously going to be inclined at an angle, and we use a specific sign convention to quantify that inclination. Okay, the theta is always subtended in the counterclockwise direction as shown. And we also have the habit of creating something called the normal and tangential coordinate system, so that the force P, which is in fact acting along the positive x-axis, can now be resolved into the perpendicular axis, which is the normal axis, and the tangential axis, which will correspond to the parallel of that face. So it is possible to resolve the value of P as shown by the green arrow in the normal direction, and the value or the magnitude of that force is simply P cos theta, and the value of the force in the parallel direction of the plane, which is V, and that value can be given as minus P sine theta. Okay. So one very important concept that you have to grasp here is, when you're not dealing with a plane that is perpendicular to the plane of the prism, there can result a change in the cross section that is actually trying to resist that force. So here in this case, this red block you see is in fact the cross section when you have taken a perpendicular plane to the face of the prism, while that white face you see is the face of that inclined plane. So there is definitely a change in the resisting cross section, and hence we should see a corresponding change in the value of the stresses of that material when we're considering that plane. So this simple animation is actually showing you the way that that cross section can change as compared to the normal cross section. when you cut a plane anywhere else. So we now try to use the force and the change in the cross section of this new plane to calculate the stresses in those respective directions. So we begin by first calculating the normal stress, which is simply given by the force component in that direction divided by the cross section of the plane, and it is possible to reduce that expression as sigma x cos square theta. So that is the value of the new stress that is acting perpendicular to that new arbitrary plane that we have taken. In a similar vein, when we consider the force that is acting tangential, because it is along the surface, we term that force as the shear force, and hence there is a corresponding shear stress acting along that surface. And the value of that shear stress is simply the value of that shear force divided by the cross section upon which it's acting. So that boils down to minus sigma sine theta cos theta. So in this fashion, it is possible to see how the magnitude of the stresses actually change depending upon the orientation of the plane. So what I'm trying to get at is, though you may have performed a simple, purely axially tensile specimen, the kind of stresses that can prevail in that member are still possible to be in different directions. Okay, so this concept is very important as we are now going to move forward and talk about the concept of stress tensors, where we want to see the behavior of any given element in a material point. Okay, we are soon going to talk about displacement fields and how these displacement fields actually create a stress field, and how we term that internal reaction that any material gives to an externally applied force as something called the von Mises stress condition. Okay, so this concept of von Mises stress is in fact a very important fundamental quantity that we are now going to spend some time about. Okay, but before we go to that point, this will be followed by a brief session where I will show you the way that we solve problems when there are different forces acting in different directions, and how we use this framework that we have shown now to try and find out the stresses in the tangential and the normal directions. Thank you.